This is February-March paper 42, 2023. First question is define the gravitational potential at a point which is work done and bring, and this is a common definition that we all need to understand and we remember. The point of taking it from infinity is that the potential value that is going to be negative gm over r, this has to be so high that this becomes zero, and that is how we look at gravitational potential. It always starts from infinity and then we bring it up to a certain point. So Artemis is a spherical planet. Okay, fine. We are also familiar with this graph as well. This is the distance from the center of the planet, and where we see the graph ending abruptly, we can assume that this is going to be half of the planet, and the rest of the planet, or the half of the planet, is going to be like this. So this is approximately the radius of the planet. This is, of course, in light of, in reference or in discussion of other questions that you might encounter. So I'm just going into little tidbits of the rest of the questions that you might encounter. And of course, definitely this is potential, and the formula for potential is going to have a negative sign, as phi is equal to negative gm over r, right? All right. So then Artemis has the radius of it is already given to us. Otherwise, sometimes you have to read it from the graph. Determine the value phi on the surface. So when you come close to the surface, this is going to be the value. And if you count the number of boxes properly, you will realize that this is going to be negative 3.55 into 10 raised to power 7. This 10 raised to power 7 comes from this graph value. The next part is show that the mass of Artemis is 2.55 power 24, which is easy to do because the formula of potential you already understand is going to be negative gm over r. So it's just a matter of replacing the values. We already have the value of phi from the previous part, and we already have the value of r from the center up to that point. You can also choose to use a different value. For example, let's say this one or either this one. But it serves no purpose because we have already found one value at a given value or at a given situation. So it will be a good idea to use that value which has already been given to you. So this will be negative 3.55 into 10 raised to power 7 equals to negative because of the formula, and then the gravitational constant, which is 6.7 minus 11, the mass of the planet which we're supposed to find out, and r is 4800. Now please notice that this is kilometers. So this has to be converted into meters. So I'm multiplying the prefix of kilo over here. Once you solve this negative sign, of course, definitely we can see this is going to get cancelled out from both sides. We're going to find the value of m. The mass of the planet is going to be equal to 2.55 into 10 raised to power 24 kilograms. Now, one thing you can do is in these questions, since you are required to show that the value of m is going to be this value, if somehow you get stuck in these parts, you can put this value into this equation, and just in terms of rough work, in terms of working for yourself with a lead pencil, you can figure out which value you may be missing out on. For example, if you figured out what phi is going to be, but you don't know what r you're supposed to use, you can put in this value over here and get an answer or get an idea what r is supposed to be for the students who are still confused about the value of r. Right? So this is just as a last resort. If you're unable to solve, if you're unable to foresee what is supposed to come here, then you're supposed to do this. But because this is going to take a lot of time, so I highly recommend to avoid this until you're not left with any other option. Of course, this is a one mark question. You can leave this if you know how you're going to use this value in the next part, right? So it's a matter of choice and carefully selecting your battles. Which question you think you can do, which questions you can't do or think are going to consume more time and resources from you. Then is the third part, calculate the gravitational field strength. Now again, there is a standard formula for G, which is gm over r squared. It's simply a matter of replacing values. If you were unable to solve the previous part, then you can simply use this value because he asks you that show that the mass is this, and if he says that the mass is going to be this, then that is going to be its value. So 6.67 into 10 raised to power minus 11. Then the mass is 2.55 into 10 raised to power 24. Divide this with the r square. Please be careful. This is again going to be 4800 into 10 raised to power 3 whole square. So the value of G comes out as 7.38 meters per second square, or newtons per kg, as gravitational field strength. So up to two significant figures, this is going to be a 7.4. In the next part, he says the satellite is orbit on a fixed position above the. Now this question, when he says it is orbiting on a fixed position and most likely above the equator. So that means the satellite is above the equator. This is the key word. It is most likely, this is actually a question of geostationary orbit, right? And for that, I've also recommended to memorize a proof. So what we can do over here to calculate the period, it's a 4-mark question. So the examiner expects you're going to make a statement over here. So you can write down, or you can just simply say that the gravitational force is providing the necessary centripetal force. You can write this down in English as a word statement over here, or you could just write down it straight away as a formula. So the gravitational force formula comes like this: gmm over r square equals to the centripetal force over here that we're supposed to use is mr omega square. Now, centripetal force also has a formula of mv square over r, but why are we not using that? We could have used this as well, but it will increase the number of steps. Since we're looking for a time period, only omega is equal to, or angular velocity is equal to, a formula that is 2 pi by t or 2 pi f. So in favor of reducing the number of steps, I'm choosing this option, right? Okay. So now we can notice some things straight away. The small mass, or m, gets cancelled out. Let's bring r over there. So this becomes gm equals to r cube omega square. And let's replace, in place of omega square, let's replace 4 pi square divided by t square. I've already taken the square, so that's why I can reduce the number of steps I'm going to take. Right now, it is just a matter of replacing values. So I'm just going to write the values over here. So g is gravitational constant 6.7 power minus 11. The mass of the planet is 2.55 into 10 raised to the power 24 equals to r cube. Now, where is the value of r? How do you get the value of r? Notice that in this question, he says the gravitational potential is negative 0.65. He's already mentioned where he wants to observe, or where the gravitational or the geostationary orbit exists. Now you have to go back to the figure over here. Now notice that these distances are given to you from the center of the planet itself, right? So at negative 0.65, I will read the graph at somewhere this location, and please use a lead pencil and draw a dotted line to show the examiner that you are picking up a value from this point. So it seems to me, it looks like you can count the number of boxes and realize what the value of r is going to be, right? So it looks like that this is going to be up to, you can count the number of boxes, and it's going to be 2.6. Of course, this is just a rough estimate. It should come along at this point, but at negative 0.65, we see that the value is going to be this one, according to my number of boxes calculation. So please draw the dotted lines. Then over here, we see that r is actually 2.6 into 10 raised to the power 7 whole cube. Don't forget about the cube. Then we have 4 pi square divided by t square. Now, a good practice would be that if you have written this equation down, then please bring t square over there and exchange them with this whole fraction in the divider, in the denominator, right? And don't forget to take the under root at the end. So the time period of this equation is going to be in seconds, because all the values are in standard form or in scientific notations, or you can say they are in standard units. So your answer is going to be in standard unit as well, and that is going to be seconds. So 63871 seconds is my answer. Now, so he's asking us about in hours. So you have to divide this with 3600. Why? Because 60 seconds multiplied by 60 minutes is going to give you, or is going to make you move towards hours. So this is going to come out as a time period as 17.7 hours. Up to 2 significant is going to be 18 hours. The next part, he says, state one similarity, one difference. So one of the similarities will be that both of them are 0 at infinity and are inversely related. You can choose either of them. How do you see that? Because it's about gravitational potential and electric potential, so write down their formulas. So gravitational potential phi is equal to negative gm over r. We can clearly see that if you increase r up to an infinite value, the value of phi becomes 0. So phi at r equals to infinity becomes 0. Also, the formula for potential is q divided by 4 pi epsilon naught r. So even in this one, we can see that potential, or the V at r equals to infinity, becomes 0 volts. This becomes 0 joules per kg, right? So this was the first similarity, that they become 0 at infinity and are inversely related. We can also see that with the respective quantity, of course, that phi is inversely related to r and potential is also inversely related to r. So more like V is inversely proportional to r and phi is inversely proportional to r. right? In the next part, we have, so we have justified these 2 points. The difference is gravitational potential is always negative. You can see that since it is always negative, the negative has become a part of the formula itself. But potential can be positive or negative depending upon which charge you are talking about. Primarily, if let's say you're talking about a positive charge and you're also bringing in a test positive charge close to this, the potential would become positive because both charges are positive, right? And if you're talking, let's say, about, now that is potential energy, but if you're talking about, let's say, a negative charge, or if you're trying to calculate the potential of the negative charge, since you have to put in the negative sign over here in the formula, this potential will become negative. And similarly, if you bring in a test positive charge close to this, even then the potential energy will become negative, right? So gravitational potential is always negative, whereas electric potential can be both, or is going to be positive and negative depending upon the situation. The next part is state what is meant by an ideal gas. So a very simple and straightforward repeated question. So a gas that obeys ideal gas laws. What are those ideal gas laws? Basically, the equation that you've done is PV equals to nRT. But why are we not talking about N and R? Because N is the number of moles and we believe that's a seal-tight container. The number of molecules, the number of particles will not change, and R is a universal gas constant. So what are we left with? We are only left with an equation that has these 3 variables to change or expect to change amongst them, right? So that is why we have only written down that ideal gas would actually, or the law is actually PV equals to K or temperature. Then you add a comma and explain what P, V, and K are going to be. So P, of course, write this down in English. P is pressure, V is volume, and K. Do not write down K as only temperature. Please write down thermodynamic temperature because thermodynamic temperature scale is in Kelvin, right? So examiner does not know what temperature you're talking about unless you say it's thermodynamic temperature. So part B says a fixed mass, a fixed amount of helium gas. So that means that there is no leakage. There is no leakage, and N, the number of moles, will remain constant. So it says primarily it has this initial state, and then it has a final state that is going to look like this one. He says that it is compressed probably. Now we can see that it is being compressed. The volume was 540. Now the volume is 30. We can also observe a few other changes, that the pressure has increased, right? Which goes with this formula that if you increase the pressure, or if you compress it or try to compress it, the volume is going to get decreased. So it looks like this. Plus, we can see that the temperature of the gas has also increased, right? This comes from the idea of this one, and all of these equations are PV equals to T, right? So if you increase the pressure, temperature has to increase, or the temperature might have increased because of increase in pressure. I will also show you an animation of this, but we have to get to the last part first. So he says show that the helium gas behaves as an ideal gas. Now for any equation or any system to behave as an ideal gas, the thing that you explained previously, that it should behave PV equals to K, should be applicable on both situations. So PV equals to temperature T, for example, of the initial situation, and PV equals to T of the final situation. They both should produce the same answers. So if you rearrange this equation, this is going to become PV divided by T, and for the sake of understanding, let me write down as P1 V1 T1 to represent an initial situation, and let me write down P2 V2 over T2 to represent, not T square, sorry, this is going to be T2 to represent a situation after some change, or in another situation. They both should produce an answer that is going to be a constant. That should be a constant. So what you're supposed to do for the examiner is solve for both systems and then show that if they're going to get the same answer, if they're both giving you the same answer, they're equal, that means that they're going to behave like an ideal gas. So to simply put, I'm going to erase this. To simply put, you will realize that P1 V1 over T1 should be equal to P2 V2 over T2. They both should be equal. So just have to put in the values and explain to the examiner that this is how it's going to be. So P1 is 1.1 into 10 raised to power 5. Volume is 540, and please realize that this is centimeter cube and the volume is supposed to be in meter cube. So 540 divided by 100 cube divided by the temperature is 27 plus 273, as thermodynamics should be equal to the after situation, which is going to be 6.70 into 10 raised to power 6 multiplied by volume, which is 30 divided by 100 cube divided by 742 plus 273. Now you will notice that both answers, this is also going to be 0.198 and this is also going to be 0.198. So calculating 0.198 is necessary. This is also important, and then you simply write down your conclusion over here that they're both producing a constant value. They're both producing constant value, hence it obeys ideal gas laws, right? Because if it hadn't, then there would be something different in the primary, initial state, and the final state. Okay. All right. In the next part, he says, using the first law of thermodynamics, that is going to be expressed like this. Okay, fine. We already know that. Use the first law to explain why the temperature of the helium gas may have increased. You see, when you compress a gas, you're adding energy into the system. You're doing some work on the system. So in this scenario, where does that come from? You see, this W represents P delta V. So if you're adding energy, if you're compressing the gas, you're adding some energy into the system, which is going to be positive. So W, or the change in W, is higher, or it is more as compared to before. It is producing a positive value. And that positive value, since it has to justify or satisfy the equation, some of that energy or some of that work done is going to go into heat, and some of that is going to go into the change in internal energy, because we have to maintain this equation, right? So it's possible that, for example, W is 100, then Q becomes 40, and delta U becomes 60. So the whole system or the whole equation has to be justified like this, right? Okay. So some of it is going to be added into one factor, some of it is going to be added into another factor. So we have explained this over here as work done during the compression causes the internal energy to increase. This is your final conclusion. This is your final answer, right? And then you explain this to the examiner that this causes an increase in kinetic energy of the molecules, which causes an increase in temperature. And you can simply write down the delta U is positive. The change is positive. Now let me show you an animation regarding this that will show you something similar. Now over here in this I'm not playing this animation right now. I'm just writing this down, right? So this is our initial situation, right, as taken from the question, and this is our final state, again taken from the question. Now you will notice that if you let this animation play, I'm going to compress the system. You can notice two things at the same time right now. Please notice that what is the temperature and what is the pressure. The pressure is in terms of atmospheric pressure. You can convert this in kilopascals, so it does not matter. So right now we are at standard conditions, the initial situation. The values are not same because the animation is taken from another computer system. So don't worry about it. Just observe what happens if you compress it. Now to play the animation, so notice that the atoms are moving. Now as you compress the system, notice what is happening to the temperature. You see, previously the temperature was somewhere around 223 Kelvin, and now it is 609 Kelvin. And previously the pressure was approximately 25 atm, and today it is 101 atm. So not only that the pressure increased, but also the temperature of the system also increased. So this is what is actually happening in the situation, that your compression has produced two changes, right? I hope that we understand this idea in terms of the animation itself, right? So let's move back to the question. All right. Then we have the third part. This is an interesting equation and an interesting question. He said that average translation kinetic energy is given by EK equals to 3/2 KT. Now this is definitely equal to 1/2 m RMS C square. And we do a proof of this as well, which proof is also important. So please go check out my videos of thermodynamics and ideal gases. I've explained this proof to you. Please memorize these proofs. This is going to come to you in 3 to 4 marks question. If not in this paper, then in some other paper. So what's the good thing about this? The good thing about this is that this 1/2 mc square is regarding one molecule. This is just one molecule. And this equation represents the whole system. So if I have the information about one molecule, what is its mass and what is its speed, I can comment about the temperature of the whole system. Imagine that if you have a room, an infinitely large room, you know a very small information about that room, that the molecules existing to this or in this area are moving at, let's say, a certain speed or have a certain mass. Can we comment about the temperature of the rest of the room if it's in thermal equilibrium? Yes, we can do that. So the equation is very powerful in terms of visualization. That's why we have done this equation. Okay. So let's see what the examiner is going to ask you. It says where K is Boltzmann constant, we understand that. Now notice how he mentions thermodynamic temperature or temperature. He says it's thermodynamic so that you can write down this in terms of Kelvin. Calculate the change in total kinetic energy of the molecules of helium gas. Now, of course, we understand that the temperature has changed from 27 to 742. And this change of temperature is only represented by the kinetic energy. So he's asking you about the change. So we only discuss the change, right? So first we use the kinetic energy formula that is given to you conveniently. So this is going to be 3 by 2 into Boltzmann constant, which is 1.38 into 10 raised to power minus 23. And temperature in Kelvin is going to be 742 minus 27. Now notice, why am I not converting this into Kelvin scale? You see, even if you do that, let's say this is going to be a change in temperature. So this is T final minus T initial. So if you write down 742, this is 742 plus 273 minus 27 plus 273. Now when you do that, this negative sign gets multiplied by this number. So this 273 gets cancelled out. You're only left with 742 minus 27. That is why in that chapter we conclude that the change in temperature, for example, the change in temperature in terms of, let's say, change in degree centigrade will be equal to the change in Kelvin, because no matter what you do, algebraically speaking, this 273 is going to get cancelled out. That's why we are directly taking the degree centigrade as a change, right? Okay. Now this is for one molecule. This information is for one molecule. It's asking you about the whole energy of the molecules of the helium gas. So we're supposed to account for that, right? So I need to multiply this number with number of atoms, or the number of molecules. Where do you think we're going to get that? So we have another equation of standard state, that is PV equals to NKT. N is the number of atoms, N is the number of molecules, right? So I'm going to make that the subject of the formula, and we realize that KT can be taken over there, and this is what the equation looks like. All right. Okay. So then we have to take these in this formula. Okay. So let's replace this over here. So this is going to be PV divided by KT. Now this PV divided by KT, it could be for any other situation. It could be for the initial state. You could use the data of the final state. It would not matter. Okay. So I'm using the data for the initial state. It does not matter. So I'm going to write down PV divided by KT. So pressure of the initial situation was 1.10 into 10 raised to power 5 pressure. Volume was 540 divided by 100 cube divided by KT, which was the Boltzmann constant 1.38 into 10 raised to power minus 34. And the temperature is 27 plus 273. So of course, this is your number of molecules and how many number of atoms are there. And this is the energy of just one atom, right? So you multiply this and you get the answer as 212 joules. So this is going to be 210 joules up to two significant figures. The next part is the mass of nitrogen. Okay, fine. This is a question from the heat capacity chapter. It says the mass is 24 grams, initial is 27, finally boiling point is 196, and condenses to a liquid. So there are two things happening. So he wants you to find the total energy. Okay, fine. So the total energy will be calculated as the energy or theta of change in temperature while maintaining the same state plus the energy coming from the change of state. Can we recognize where these two changes are? So the first change, the change in temperature, the formula for that is mc delta theta or mc delta t, plus the change of state formula is ml, right? Now first we realize that the change in temperature is actually in the first statement. He says its temperature decreases from 27 and goes up to minus 196. This is going to be the first change. The second change of state is read in this line, which is over here, that assume all gas condenses. The condensation is a change of state. It becomes a liquid, right? So there are two energy changes happening in this question. So it's a matter of putting in the values. So, and also notice that the mass is in grams, the values are in kilograms and kilograms. So we have to convert this into kg. So 24 divided by 1000. Of course, you can take mass as a common answer on the outside, but I generally avoid this because it causes for confusion, right? Okay. So what's this heat capacity? Heat capacity is 1.0. Notice it's kilojoules. So I'm going to open this up as 1040, or you can simply write down as 1.04 and keep the kilojoules over there because the final answer is also in kilojoules, right? So it wouldn't matter. And delta T is from 24 to minus 196. Now it may confuse you, but you have to add these numbers together. Why? Because if you visualize the number scale, let's say this is 24 plus 24. This is going to be 0 degrees centigrade, and way down below is going to be 196. If you're looking for the change in temperature, then definitely this is the delta T, right? So in 196, you'll have to add the 24 as a change, or if you don't understand this number line, you can simply write down as final minus initial. When you do that, your negative sign will be compensated automatically, and you will see that both numbers are going to get added together. So this becomes 196 plus 24, or to a more simple mind, this will become minus 196 minus plus 24, the final temperature minus the initial temperature. Again, notice that they're both becoming negative. So it's going to get added together. And do I need to include the negative sign in the question? No, I don't need to do that. Why? Because he's asking me himself that how much energy is removed. So I already know this is going to be a negative sign. It's going to be a negative answer because it is being refrigerated. It is being cooled down instead of heating up. So the next is change of state. So 24 divided by 1000 to convert it into kilograms. And then we have to look at the latent heat, which is 199 kilojoules per kg. Again, it is in kilojoules, so I don't need to convert this into joules to use a prefix. Once you solve this whole equation, this answer is going to come out as 10.3. And for those who used a prefix into 10 raised to power 3, into 10 raised to power 3, their answer will be into 10 raised to power 3. But again, you won't have to write down 10 raised to power 3. This is another trick that the examiner did this time. You don't have to add this, because if you write down 10.3 into 10 raised to power 3, then they both get combined and this becomes 10 raised to power 6. That will be wrong, right? So please be careful about this. All right. Question number 3 is from simple harmonic motion. I'll also show an animation for this graph that is drawn over here. And let's start with this question. Okay. So it says that it oscillates up and down. Let me show you an animation how it is oscillating. Notice how the mass is moving up and down. You can ignore the graphs for now because that's not the main topic over here right now. So notice that the 100 gram is oscillating up and down. Okay, it has been slowed down for your convenience. All right, so this is how this object is going to move. So there is going to be a maximum top point. There's going to be a maximum low point. And the central line is actually your mean position. And the amplitude is going to be referred as x dot. The maximum amplitude, how high and how low it can go. This is a graph. He says energy E with reference to X. All right. So there is P, there is Q, and there is R, right? So we have to recognize where these systems are going to have these energies, which is the next question. He says, state what energies they are. So P is total energy, Q is gravitational, and R is kinetic. Wrote this down in on a side note on a paper because I'm going to discuss this graph with you right now. I'm going to zoom out. You can see the whole graph over here, right? Now notice that during the oscillation, the energy E, P, that is the total energy, is actually a sum of, energy is actually a sum of kinetic energy plus gravitational potential energy, right? That is the gravitational potential energy. It's a sum of that. Now, when you move to the extreme positions during the oscillation, either the highest point or the lowest point, the object has to come to a stop. It stops moving. As you can see in this animation, if you let it run for a while, you can see that when it goes to the lowest point, just about over here, it stops moving. It's not moving right now, right? So if it is not moving, the kinetic energy is going to become 0 because that is half mv squared. If there is no velocity, there is going to be no movement. So which graph is representing 0 energy on the extremes? That is your graph R. So R becomes 0 at extremes position on both scenarios. That is why R is representing kinetic energy. That is half mv squared. It's not moving. Now, gravitational potential energy becomes 0 at the center, or you can say it changes shape, right? Now, notice that the gravitational potential energy, the Q graph, is maximum at the extreme points. It's maximum at these points. Why is that so? Why is that the case? You see, when it goes to the highest point, let's say in this animation, it is at the lowest point right now. When it goes to the highest point, it has the highest gravitational potential energy, right? And when it goes down, it comes down to the lowest point. Again, it has the highest gravitational potential energy in terms of the mean position. At the mean position, if you come at this point, at the mean position, this Q becomes 0. Why? Because the change, although there is a negative displacement, again, even with the negative displacement, it is going to have some potential energy, right? So at the mean position, we consider it to be 0 because all the gravitational potential energy has been converted into kinetic. So And how does the total energy become total? Because we are adding both energies. So pick any displacement. Let's say you pick this displacement, you go up to this graph, you pick this value, and then you go up to this graph and you pick this value. Add this x and y, you will get an answer of this number, which is probably, according to my calculations, is 6.4 millijoules, right? So no matter what location you pick out, they are both going to get added together and then become the total energy. That's why the total energy is constant. It does not change because it's always getting added together. And in an ideal situation, it does not matter, right? So because no energy is being removed from the system. Okay. So let's zoom back in and see what answers do we get now. Okay. So as the object has a mass of this, determine the period of oscillation, no matter, no issues. So we have from the formula of kinetic energy, that is half mv square, and v square is replaced as half m omega square x naught square minus x square, right? So where does this equation come from? Now v, velocity, is actually omega plus minus under root x naught square minus x square. So when you take the square of this to put into this formula, you get rid of the under root, but you put a square over the omega, right? That is where the equation comes from. So since he's asking is the period of oscillation, so I need the omega over here because omega is equal to 2 pi by t. That is important. Do I have a kinetic energy? Do I have some situation, some place where I can pick these values up? Yes, we do. So for kinetic energy, let's say we can choose the maximum kinetic energy. And where does it get the maximum kinetic energy? You see, R was the graph of kinetic energy. At extreme positions, it is 0. But only at the minimum position, at the midpoint, when it crosses the boundary of the mean position, you can see right about now, when it crosses the dotted line, the mean position, it has the maximum kinetic energy. Why? Because there is no restoring force. It either has to go up or it has to go down. It's not compressing the spring. It's neither spreading it out. It's not expanding. It's neither compressing. So no energy is coming from the spring. All the energy is actually from the, in terms of the speed itself. So passing through the mean position, it produces maximum speed. Now, so I choose the value when it is at the center position, at the mean position, because at that time I know that the total energy is purely in terms of kinetic energy. There is no potential energy, or there is minimum potential energy. So choosing that point gives me an answer from the graph is going to be 6.4 into 10 raised to the power minus 3, 1 over 2, mass is 130 grams, so converting this into kilograms, 130 divided by 1000 into omega, which is 2 pi by t whole square, into, since we are dealing with the maximum velocity, maximum speed, this x variable becomes 0. Why? Because x is taken from other positions. Now x naught is the maximum amplitude. X would be an amplitude other than the maximum amplitude. So when are we supposed to carry out, when are we considering this to be maximum kinetic energy or maximum energy or total energy becoming kinetic energy? Is at the mean position, is at the central position. So the central position, if considered, then the x becomes 0. There is no x, there is no displacement. That is why this equation, or from this equation, x, or the current displacement, becomes 0. Or you can say we're considering the velocity at the mean position where the displacement is 0. So x naught, or the amplitude, the maximum amplitude, is 0.015 whole square. Read from the graph. Okay. All right. 0.015 over here. So when you solve for t, please don't forget the square. Don't forget to take the under root. This comes out as 0.30 seconds. So this will be 0.30. State the cause of damping. Damping is light, critical, and heavy. This one, in this situation, the damping is due to the resistive forces due to drag or air resistance as the mass moves up and down. And some of the energy is lost due to heat in the compression and expansion of the spring, but that's not required over here. He says a light card is attached to the object. Okay, fine. So light damping, and the object is displaced with the same initial amplitude than the released and then released. During each complete oscillation, it reduces its energy by 8% of the initial situation. Determine the decrease in total energy in millijoules of the system after 6 complete oscillations. Now this may be confusing, but don't worry, I have added a graph to explain this completely. So let's go to this graph. So this is what the oscillation graph looks like to you over here. So let's plug in the values, the basic values. So let's consider this to be the maximum energy. So this is our maximum amplitude A0, which produced a total energy of 6.4 millijoules. Now, this is my first oscillation. This is my second, third, fourth, fifth, and sixth oscillation, right? So if at the very beginning, let's say the energy was 6.4 millijoules, and at the next stage over here, I'm only getting 92% because I have experienced a loss of 8%. In the next stage, a further loss of 8%. And then in the next stage, a further loss of 8%. So the question is not exactly straightforward. Let's solve it for 2 stages and figure out a pattern. Where do we see this happening? And where is the question supposed to go from here? So let's consider the starting point to be the maximum energy, 6.4. How much energy do you think is left at this point out of the first oscillation? So can we say that only 92% of the initial energy, which is 6.4 millijoules, is left? So let's call this the first oscillation. So T1 or oscillation 1, let's replace this. So after O1, I only have 92% of my initial 6.4. I'm ignoring the millijoules to save writing space. In the next stage, we see a further decrease of 8%. So can we say that this stage is actually 92% of the initial situation? Because for this second stage, this is my starting point. So I further reduce the energy of already reduced energy of 6.4 joules. Then for the next stage, I realize there is another reduction of 8%. How do you cater that? So I'm left with 92% of my initial situation. So I can see that the 92% is getting compounded. It is adding, or it is being multiplied again and again for the incoming situation or the scenario, right? So up to sixth oscillation, I can see that 0.92 is going to come into the equation 6 times. 0.92. This is going to be a part of the system in 6 times, all multiplied by 6.4 millijoules, or the initial start of the energy. That is why we can see, or we can calculate, just a moment. Okay, so we can calculate that the remaining energy after 6 oscillations is going to be 0.92 6 times multiplied by the original energy 6.4 millijoules. So this answer comes out as 3.88 millijoules. So this is the amount of energy left in the system if you were to calculate this and you reach this point. Let's say you reach the 6th oscillation. At this location, the total energy will be 3.88 millijoules. And at this location, at the very beginning, the energy was 6.4 millijoules, right? Okay. So if that is the energy remaining in the system, so how much energy was lost? So lost energy would simply be energy at the start, which is 6.4 millijoules, minus energy today present, which is 3.88 millijoules. So when you subtract this, this comes out as 2.519 millijoules, which is going to be 2.5 millijoules has been lost after 6 oscillations, reducing 8% energy as compared to before. So the next question is state Coulomb's law. Electric force is proportional, and of course we are actually explaining Coulomb's law as Q1 multiplied by Q2 divided by 4 pi epsilon r square. So product of forces, electric forces product proportional to the product of not forces, of charges. This one, and it is inversely related to the square of separation, which is r square. It's very similar to gravitational potential. The next part, he says sphere X is supported by this, and we can see that in this scenario, if this is positively charged, this is positively charged, there will be a force of repulsion among both charges, right? Okay. All right. So we have this scenario. There is a length given to us. There is also another length given to us. So we can most likely figure out this theta. These are preemptive ideas even before solving the question. I'm just picking out the values to see if they give you a hint in the next part. So the length of the thread is 1.2 and the center of mass is separated by 0.08. Okay, fine. We have read these values successfully. Now we move on. So in figure 4.2, draw and label all the forces acting on sphere Y. So when you talk about all the forces, we have to be clever about this. We have to recognize all the forces. So there is going to be a force of tension on the thread. There is going to be a force of electrical force due to repulsion between positive charges. There is going to be a force of weight on the object itself, right? Okay. So moving on to the next part, he says determine the mass of sphere Y. This is an interesting question and requires a bit of an understanding. So let's figure out the component. So this is going to be the component of tension. And if you consider this just to be theta, then we can see that this is our weight, which is going to be equal to mg. And the electric force was in this direction, which was Fe, right? So if you divide the component of tension, this component of tension, then you recognize that there are going to be two factors. There are going to be two components. So in this direction, we have a T sine of theta. Yes, T sine theta. And this one, this component is going to be T cos of theta. Let's recognize which component is equal to which component or responsible for balancing which component. So T cos theta is in the upward direction, is going to be balanced or is going to balance out the weight. T sine theta is towards the left side, is going to be as a cause or due to the electric force from Newton's third law, right? So, or to balance out the electric repulsion. So first step is to figure out this theta angle. So first step, so theta would simply be a trigonometric ratio, because we know that this length is 1.2 meters and this is 0.08 meters. So by the looks of it, this is a very long length, this is a very small length. This angle theta is going to come out as a very small value, but this is a preemptive idea again. So this will be sine theta equals to 0.08 divided by 1.2, taking sine inverse over there. So theta comes out as 3.82 degrees. I'm going to take theta up to 3 significant figures until I reach the end of the question. The second step of the question would go towards figuring out what is the electric force. So that will be equal to T sine theta, right? Because I need to find out the value of T, tension. Once we have the value of T, we can figure out the value of T cos theta and ultimately find the mass of the sphere. So finding T is important, which is going to be found by T sine theta and electric force. So T sine theta is equal to electric force, which is Q1, Q2 divided by 4 pi epsilon naught r square. Now, we don't know the value of T, but we know the value of sine theta. So this will be T sine of 3.82 equals to. Now, the product of charges is 96 into it, since it is nanocoulomb, so minus 9 into 64 into 10 is to the power minus 9 divided by 4 pi epsilon naught is 8.85 into minus 12, and the distance between the charges is this one, which is 0.08. So 0.08, please don't forget the square, take the square and take sine theta over there to get divided. So T comes out as 0.1295, which is equal to 0.13 newtons. So now I know that the value of T is actually 0.13 newtons, this value. Now we can make the component or choose the component of T cos theta and equate this, because it is responsible for the weight, as W equals to mg, equal to that. So in the third step, we have T cos theta being equal to mg. We want to find mass. Let's make that the supply of the formula. So m equals to T, which is 0.13 into cos of 3.82 divided by the value of g, which is taken over there. So 9.81. So mass comes out as 0.013 kg. Okay, it is just a lengthy question, but it's a good one. The total electric potential between X and Y. Very easy question. So potential is voltage equals to work done by charge. Since asking me about potential energy, I have to take the Q over there. So this becomes V or delta V multiplied by Q equals to work done, or is equals to energy. So energy between them or work done between them is going to be equal to change in potential or the current potential due to any one of the charges, right? So I am choosing this to be my standard charge, and for this charge to bring 64 nanocoulombs from a distance of, let's say, at infinite distance, it was already placed 64 nanocoulombs. Today, it has been brought so close that their distance between them is 0.08. So the distance for potential from infinity up to that point will be r minus infinity or r minus 0. So this is 96 into 10 to the power minus 9, because the formula for potential V is equal to Q divided by 4 pi epsilon naught R. If you multiply this with the charge that you're bringing close to the first charge, then that becomes potential energy, right? So this will be 4 pi epsilon naught is 8.85 multiplied by, since we're talking about energy, we have to multiply the charge you brought closer to the first charge. So the second charge that was brought closer was 64 minus 9. Now, would it matter if you change the perspective? If you want to look at it from the perspective of 64 nanocoulombs, that 64 was already there and 96 was brought from a distance of infinity where potential V was equal to 0. Would it matter? No, it would not, because if you look closely, these both numbers are being multiplied. It is primarily Q1, Q2. So it doesn't matter whether you change the perspective. It does not matter. That's why he is leaving it to you. What is the potential between X and Y? So when you solve this, this comes out as 6.91 into 10 to the power minus 4. So this is 6.9 minus 4 joules. The next question, he says there is an electron with the 250 18 millimeters. Okay, fine. So we can figure out that the electric field strength between them should be V by D, or can be force divided by charge. This is the formula for electric field strength, right? Previously, this formula used to be in AS and this formula used to be in A2 and AS both. So they've removed it from AS now, and they've completely added the whole concept of electric charges in A2 only to avoid confusion among the students. So he says, state the direction of electron or electric force. It is towards the plate P. It is going to experience a force in the upwards direction. Why? Because the positive plate is upwards and negative plate or 0 volt is on the downward side. Electrons are negatively charged and the plate positive has a positive potential. So as soon as it enters at this location, it will experience an upwards, perpendicularly upwards force towards plate P. So that's why don't write down upwards or downwards, write down which plate it is going to be pushed towards. Determine the magnitude of the force acting on the electron due to electric field. No problem, very easy, because electric field is equal to force per unit charge. Replacing this over there, this becomes force equals to electric field strength multiplied by the charge you placed in it. Now for electric field strength, we have another formula of V by D for parallel plates. So we're going to replace F equals to V by D multiplied by Q. Now this V by D comes from the electric field strength, right? As discussed earlier, that they're both equal to that. It's a matter of replacing values. So F equals to voltage, or the potential difference is 250 minus 0 volts. Now please notice that if, for the sake of example, this was at, let's say, minus 100 volts, then what would be the value of this V? Then that would be minus 250 minus 100. That will become plus 350, right? So sorry, this is actually positive 250. Then the potential difference would be 350. So please notice that over here, since this is at ground voltage, this is 0, it has become 250 minus 0, right? So this will be 250 minus 0. I'm writing this out for understanding, divided by the distance, which is 18 into 10 raised to the power minus 3, converting it into meters, multiplied by the charge. Because it's an electron, the electron has a charge of 1.6 into 10 raised to the power minus 19 coulombs, right? So the electric force comes out as, if you solve this, 2.2 minus 15. So this is 2.2 into 10 raised to the power minus 15. So 2.2 into 10 raised to the power minus 15. In the next part, he says, explain why the electron does not follow a circular path. He says, now this is a common question. You see, an electron or a charged particle, be that, let's say, alpha positively charged or beta negatively charged, when they are subjected to magnetic field, they experience a circular path. Let's say this is a magnetic field, and you provide it with a positive charge or negative charge, they will undergo a circular motion. But when you place these charges or introduce them into an electric field, they undergo parabolic motion. So it's going to go like this. This is not a circular motion. And why is that so? Because the moment it experiences force, the direction of the force does not change. It is still perpendicularly upwards. Now, to explain this further, to understand this further, let's visualize an extreme scenario, an extreme case. What could be the extreme case? Just imagine if there was a very, very large distance between the plates. Let's say we had a plate at this point and we had a plate at this point. The moment electron enters in this plate, it will experience a force upwards, right? It experiences an upward force. Now it keeps on experiencing an upward force. There will come a time that the forward velocity component will be meaningless. It would not mean anything in favor or in reference to the upwards component because it is always experiencing a force towards the positive plate. So effectively, the whole path becomes a straight line path. So this path is actually called a parabolic path, right? This is also followed in the kinematics projectile motion case as well. So that is why it will not follow a circular path, because the force is not always perpendicular to the velocity vector, right? Now, why do we say this? Because for a circular motion, if this is my force, then this should be the velocity component, right? And there should be an angle of 90 degrees between them. So since they are not always perpendicular, there is not always a 90-degree answer. That is why we answer this question. And force always in the same direction, as explained earlier, that this is always experiencing a force upwards. In the case of circular motion, if the object eventually comes to this location, the velocity component is over here, the force component is over here, it comes to this location, force is toward the center, velocity towards over here, it never loses the 90-degree angle amongst force and velocity, right? Okay, and this can only happen in a magnetic field. This always happens in an electric field. You can memorize this. The next question is about capacitors. This question is particularly tricky and difficult just because he has used the LNQ function. Okay, this is the scenario given to you, the battery is given to you, the resistor and two-way switch. Okay, fine. First, what we have seen before, he charges the capacitor with the battery and then switches the switch over there to release the energy into the resistor. We have previously seen these questions many times, right? So this is a graph of discharging energy. It is fully charged, which means it will have a voltage of 12 volts when it fully charges. He says, show that the capacitance is 1.5. He's just checking whether you can identify that this is LNQ, right? Okay, so we have the equation as Q equals to CV. We want to find capacitance. We have the voltage as 12 volts. So the only thing that we don't have is Q. Where can we find Q? You see, when it was fully charged, that is the location at time t equals to 0. At the very beginning of the experiment, the very beginning, the very first moment you charge your mobile phone to the 100%, that is, and when you remove the charger, that is when time gets counted. That now the battery is being discharged into the mobile phone, right? Same thing is happening over here. So the very beginning, this is a value of 2.9, but this is actually LNQ. So LNQ or Q naught, because it's an initial value, is actually equal to 2.9. We want to find the value of Q, charge itself, how much charge is there. So taking anti-log, we can say that Q naught is equal to e raised to power 2.9. When you do that, this is going to come out as Q naught equals to 18.2. Now, what should be the prefix? The prefix is microcoulombs. So I will add the microcoulomb factor or sign over here. Then simply replacing this value over here in this formula, this becomes 18.2 into 10 raised to the minus 6 equals to C into 12 volts. So C is equal to 1.5 into 10 raised to the minus 6. So we have successfully shown that the capacitance is 1.5. Next, he says determine the value of the resistance R. Now notice that we have a component of time constant, which is tau equals to RC. So if you increase the resistance, the capacitor loses its energy slowly into the system. It delays the amount of energy, that is, or you can say it reduces the amount of current, so the capacitor discharges slowly. There are two methods to this question. I will explain both of them. So whatever you're comfortable with, you can use that in the future. So method number one, this is M1. In this, we're going to use the gradient. So first we need to use the equation Q equals to Q naught e raised to the power minus T by RC. If you take log on both sides, this becomes ln Q equals to ln Q naught minus ln of e raised to the power minus T by RC. Now this is logarithmic rules. This is going to come, this will be plus, this is going to come on the outside. So this becomes ln of Q equals to ln of e becomes 1. And this, since it has a negative sign, let's bring it to the other side. This becomes minus T by RC plus ln of Q naught, right? Okay. Now we can notice that the graph is actually drawn between ln Q and T. So ln Q is my y-axis and negative T is my x-axis. So our 1 over RC becomes your gradient, mx plus c, of course, right? So this negative sign will be considered with the gradient. So we can see that the gradient itself is actually equal to negative 1 over RC. Now, do we have the value of capacitance? Yes, the value of capacitance is 1.5 power minus 6 farads. We already have the C, but we don't know R. This is what we want to find out. But do we know the gradient? No. So the next step would be to find out the gradient. So for the gradient, we can choose any two values. You can choose the starting point. You can choose the points that I have selected for the gradient are 2 and 2.9. So this is the second coordinate that I have selected. So at this location, this value for me was 3.6. Yes, 3.6. So the first coordinate is this one and the second coordinate is this one. I'm writing them down over here. So the first coordinate was 0, 2.9, and the second coordinate was 3.6, 2. Using them, we get change in y over change in x. So 2.9 minus 2 divided by 0 minus 3.6. Definitely it's going to be a negative answer because the gradient is downward sloping. It's going to be a negative value. So this comes out as negative 0.25. So this is my gradient of the line. You can choose any other points as well. It does not matter. You can choose this one, the last point, or this point. It's okay. It's fine. It doesn't matter. So the gradient was equal to 1 over RC, negative 1 over RC. So negative 1 over R into 1.5 power minus 6 equals to negative 0.25. You can very clearly see that the negative sign will be cancelled out in this equation. Replace R with 0.25 and you find that R is equal to 2.666 and so on. Recurring decimal place will become 2.67, which finally becomes 2.7 into 10 raised to power 6. Yes, 10 raised to power 6 ohms. So this will be 2.7 into 10 raised to power 6. To explain the second method, I'm going to use the space over here. So in method number 2, this is method number 2. In this method, we can use the equation which is Q equals to Q naught E raised to power minus T by RC. So what is the present charge? You see, time T represents how long has it passed, how much time have you consumed to go from a starting charge of Q naught to a present charge of Q. So again, it's a matter of picking coordinates. I can again choose the coordinates given from the graph. It's no problem for me, right? So after 4 seconds, I'm choosing different coordinates this time. So after 4 seconds, I can see that this value is 1.9. Please count the number of boxes. So in this method, this is supposed to be 1.9 equals to 2.9 picked from previous starting point, e raised to power minus 4, because this happened after 4 seconds, right? Okay. So divided by, do I have a value of R? No, I don't. Do I have a value of capacitor? Yeah. This is 1.5 into 10 raised to power minus 6. Yes, I want to find R, but please be careful. Is this supposed to be 1.9? Are these values of Q directly given in the graph? No, they are in terms of ln. So I must take the antilog. So this is going to be e raised to power 1.9 equals to e raised to power 2.9. Antilogs equals to e raised to power minus 4 divided by RC. Now, once you take this over there and you then take the natural log, this is going to look something like this. So ln e raised to power 1.9 divided by e raised to power 2.9 equals to negative 4 divided by RC, because ln of e becomes 1, right? What you can do, since I didn't do it, what you can do is calculate these numbers manually and then add them together over here. It will make your life simpler. So when you do that, both answers come out to be negative. So this answer comes out to be minus 1.00 something equals to negative 4 divided by R into 1.5 into 10 raised to power minus 6. You replace R over there and bring it over here, and the negative sign cancels out, of course, definitely. So even in this situation, R comes out as 2.67 into 10 raised to power 7, 6, which becomes 2.7 power 6. So it does not matter. Method this one or that one. I've solved it both ways. Okay. So the next question is the energy stored at time t0. Very simple question. So energy is equal to half CV square. So 1 over 2 into capacitance is 1.5 power minus 12. Sorry, this is not minus 12, this is minus 6 probably. Yes, minus 6 into 12's square. So this comes out as 1.1 into 10 raised to power 4 minus 4. Very easy question. Part D. A second identical resistor is now connected in parallel with R. Now please, in electricity or electric current or the chapter of electric current, we understand that if you connect resistors in parallel, the overall resistance decreases, right? And there is a rule for this, that if you connect identical resistors, let's say this is R and this is R and R, the total resistance is R by 2. It divides by half. If you're not satisfied by this, since it is an identical resistor connected in parallel to this one, how will you calculate the total resistance? It will be 1 divided by 2.7 plus 1 divided by 2.7 equals to 1 over R. You will definitely, after putting in the prefixes, doing everything in your power, all the maths that you want to use in the world, you will land at an answer that is exactly half of the previous answer. So a more intelligent approach would be to remember that if identical resistors are connected, the overall resistance decreases by half. Now also, if there were 3 identical resistors, then this would be R by 3. And the rule follows so and so forth, right? Okay, so the resistance has halved. If the resistance has halved, it discharges quickly because the value for tau time constant is equal to RC. Have you changed the capacitance? No. Have you changed the resistance? Yes. So the resistance decreases, the time to hold that charge, to keep that charge inside the capacitor decreases as well. Look at it from another perspective. If you decrease the resistance of this branch, which is now half the previous resistance, when you switch over, the current flows more easily. If the current flows more easily, then the capacitor discharges more easily. Just think about a water tank. If you're just removing energy just from one tap, the water tank gets emptied slowly. If you open up 2 taps to get water, it will run out more quickly. So that analogy works over here. So I should suspect that within a time of 5 seconds, or let's say 5.1, 5.2, wherever this graph ends, I should suspect that this is going to be a much steeper line. At least twice the gradient, at least twice as much steep, because it is losing charge twice as fast. So if this was 2.9, I cannot straight away divide this by 2 and get the answer. I can't do that. Why can't I do that? Because simply put, this is an ln graph. We can't do that. Now, a more intelligent approach would be that since the gradient is negative 0.25, the new gradient should be minus 0.5, right? So how should we go about this question? So there are multiple choices. There are multiple ways to go about this. You can either simply use the gradient formula or the gradient method to solve this. Let me put that into perspective. So today the gradient is negative 0.5, which should be equal to one of the coordinates, which was 0, 2.9, the starting coordinate, and the ending coordinate should be, let's say, 5, y, right? So I'm taking this 5 as my last coordinate. I should have taken 5.2, does not matter. So 5, 0, that where would it come now? So this would be 5 y minus 5 divided by 2.9 minus 0 equals to negative 0.5. When you solve for y, this gives you an answer of 0.4. So this coordinate at 5 should be 0.4, located at over here at this location. Again, please count the number of boxes. I'm just doing this as a rough value, right? So it should be there. But if you're not satisfied with this answer, let's say if you don't accept this mentally, just for the sake of mental exercise, although this is the final answer, for the sake of mental exercise, let's do it by the equation method and see what do we get. So Q equals to Q naught e raised to minus t by RC. But what should be the R today? R should be 1.35 into 10 raised to power 6, half of the initial value, right? So what should be the charge today? So Q equals to 18.2, because of course, remember, we can't take the ln. We have to take the anti-log for this equation to be viable. So e raised to power minus t. What should be time t? I'm taking 5 as my time t, right? I could have taken 5.2, does not matter. It would still give me the same answer because I need just one coordinate, which I can extrapolate. So minus 5 divided by r, which is 1.35 into 10 raised to power 6, c, which is 1.35 into 10 raised to power minus 6. What I have done to make it simple is that I have separately multiplied these two numbers separately to avoid large numbers being added on the calculator. So this comes out as 2.025, right? Then you replace it over here, calculate this, and the Q comes out as 1.59. Can I plot this directly on the graph? No, I can't do that. So I have to take the ln of this value, which is ln of 1.5. Let me rewrite this. So ln of 1.59 comes out as 0.43, which is absolutely right, because if I go back to the graph, 0.43 will exactly be over the same point. It is slightly higher, but exactly the same point. So at 5, if I get this line, now today you have the gradient's coordinate. You have the exact mark. So this is your mark over here. Please use a ruler like this and draw a line from the starting point up to this point in a straight line manner. And that is your answer, right? So you can either visualize it from the gradient perspective or solve it for yourself to further increase the grip on this equation and idea, and know how to smartly solve this by saving time. Okay. Question number 6. Explain the observations for Hall probe. Hall probe gives the maximum value when the electric or when the magnetic fields are perpendicular to the slice, and it gives 0 when the magnetic fields are perpendicular. Okay. Is a 90-degree probe is per hand? Yes. So memorize this answer. That is how it works, right? The formula for calculating VH is this. We understand that, and please also do the proof of Hall voltage. This is also important. So he's given us the material, two materials, silicon and copper. State the meaning of N, density of charges or charge carries per unit volume. As you can see that this is in per unit volume, that is primarily meaning of number of carriers, number of electrons, or number of positive charges, depending upon copper or silicon, because if you're talking about copper, electrons are the majority carriers. If you're talking about silicon, positive charges or protons are the majority carriers, right? So number of carriers, be that positive and negative, depending upon semiconductor, depending on copper or metal, divided by the volume in which they are traveling, in which they are being held. So that is why this is that the meaning of the value of N. Explain why Hall probe is made from silicon rather than copper. You can see that from this equation, we can see that Hall voltage is actually inversely proportional to N. So it's a good idea to get the highest value of Hall probe or Hall voltage, because we want to make it as sensitive as possible by providing the least number of values. We want it to react to smallest number of changes. So I can only do that if it's a question about choosing material. So I have to reduce the number of N. I have to reduce the number of charges. Only then I will get the higher voltage. That is why, since they're inversely connected, I will choose silicon. So silicon has a smaller charge density than copper. It produces higher voltage, Hall voltage, if silicon is used for the same magnetic field, because Hall voltage is inversely proportional to number of charges. In the next part, he says that a maximum read 24 millivolts is given when the Hall probe voltage or the magnetic field is 32 millitesla. So in terms of VH being equal to BI divided by NTQ, he has given us a standard value of VH and B. He is not discussed current. He is not discussing N, T, and Q. He has given us a relationship between VH being proportional to B by these two standard values. He says that we're not changing anything else. The Hall voltage is still 24 millivolts. Okay, fine. He says this is the graph of the new situation, of the new case, because today he has placed a coil with a diameter of this much in a varying magnetic field. Which is that varying magnetic field? This is that varying magnetic field. So if he places that over here, what will be the Hall voltage now, or what will be the electromotive force introduced? Now, please notice he's asking us about the maximum EMF. If I want to find maximum EMF, I will be looking for the maximum change. Notice that Hall voltage, since it is a representative of B, right? They are analogous to each other. I should think like that. So the change from 0 up to, let's say, this value is 36 probably. Yes. So this is 36 millivolts. And this took a time of 3 seconds to do that. I'm getting the same change, 36 back to 0, the same change, but in a smaller amount of time. So which one is a greater change or a greater rate of change? This process was slow. this process was faster, or it was fast in comparison to the previous change. So since I'm looking for the maximum voltage, I will be looking for the last quarter where I see the maximum gradient, the maximum change, the maximum steepness, right? Okay. This is our preemptive ideas, yes? Okay. So let's go ahead. So for EMF, the formula that we have is standard EMF is equal to NAB divided by change in time. So N is a constant, cross-sectional area is a constant, but the rate of change of magnetic flux is not constant. It is going to be from the gradient, from the graph, right? But do we have the magnetic field, or do we have the rate of change of magnetic field? Because the graph is for Hall voltage. Yes, we do. How? Because we have understood that Hall voltage is proportional to B from the previous equation. So from this, we can say that the comparison of the first equation, or the first situation with the comparison of a second situation, can give me the Hall voltage, can give me the magnetic flux today. Do we have an initial situation? Yes, that is 24 millivolts generated at 32 millitesla. So how much voltage will be, or how much magnetic field would be generated at 36 millivolts? We can do that comparison. So rearrange this equation. It looks something like this, that B2 divided by B1 is equal to V2 divided by V1. It comes from this mathematics, right? So B2 is what we want to find out. The initial magnetic flux was 32 millitesla, equal to the current maximum voltage is 36 millitesla divided by the initial, millivolts, and the initial voltage was 24 millivolts, right? So this 32 goes over there and get multiplied. So our magnetic field today must have been 48 millitesla to cause an initial value of, let's say, 24 millivolts to increase to 36 millivolts. It could only be done if the magnetic field was increased from 32 millitesla to 48 millitesla today. So that is where we get the value of B. And how fast was it changed? You see, I can choose the first quarter or I can choose the second quarter. I will choose the second quarter for the maximum effect, for the smallest change in time. So number of turns N is 780. So 780 multiplied by the cross-sectional area 3.6 centimeter is the diameter. Please be careful. So this is pi into 3.6 into 10 raised to the power minus 2 divided by 2 whole square is pi r square multiplied by the change in magnetic field, that is 48 into 10 raised to the power minus 3 millitesla, divided by how long did it took for this to happen. So it changes from this point, which is 7.2, and goes up to 8.6. So a time difference of 8.6 minus 7.2, right? When you solve this completely, this comes out as 0.0272, which becomes 0.027. I hope you understand this. Question number 7, he says to discuss about the emission spectrum or the absorption spectrum. Dark lines. If there are dark lines, he's talking about the absorption spectrum. Okay, let's see. Yeah. So how does the dark spectrum or these absorption spectrum work? This is a topic from quantum physics, or you can say quantum mechanics, right? So what is happening at this position? What is happening over here? You see, light is being passed from a cool gas, passed from the prism to spread them out, and then observed on a screen. If you don't use a prism, you can use a diffraction grating crystal, because the purpose of both of them is exactly the same. So diffraction grating crystal opens up the wave and spreads them out like this. When you do that, it shows you all the colors that were being introduced in the white light. Your eyes cannot see what was missing, but this, when it opens up, it shows you the ingredients. Now, this is what the absorption spectrum is going to look like. There are some wavelengths that are missing. This wavelength is missing, this is missing, this is missing, and these wavelengths are missing. Where did they go? We did introduce them from the source of light. This had everything, but when it passed from the cold gas, it lost some of the wavelengths because they were absorbed. But we discussed that when they're absorbed, they're immediately emitted back out. But if they're emitted back out, why don't we get them back? There is a reason for that. So this is how the process happens. First, when there was a cold gas over here, photons were absorbed specifically for those energy levels for which the electrons can make a jump. The rest of the wavelengths were spitted back out again. They were not absorbed. Why were they not absorbed? These wavelengths, which are still shown on the screen, were not absorbed. Why? Because the electron shells didn't have that discrete energy change, so the electron could absorb them and go back up again or get excited. It didn't have it, so those photons were not absorbed. So they were exactly transmitted through the cold gas, spread out by diffraction grating crystal. They were not absorbed. But for those who were absorbed, let's say, those who were absorbed, they stayed in a certain shell and then they got back out again. They were re-emitted by de-excitation of the electrons from high level to low level. And if the electron has to come back, it has to release its energy in terms of a photon. Now, when these photons are emitted back again, why don't we get them back? We don't get them back because these emissions are now in random directions. You see, in terms of an atom or electron shell, they absorb this energy, they get excited, they then de-excite themselves and release the photon in random energy. They are now released in random directions. So previously the photons were being received in a straight direction. So the ones who were not absorbed got received on the screen, and the ones who were absorbed but emitted in a different direction didn't make it to the screen. They couldn't go there. Since they were not received at the screen, they appear to be as dark lines on the spectrum. We didn't get them back because they were emitted in random directions. This is the idea. This is the answer for that. So this is how we write it down. Photons are absorbed, electrons are excited, they go up a shell. Then photons energy is equal to the change in energy levels as discussed in energy shells. Photon energy levels emit only one single lambda or one single wavelength, because if they get excited, they come back and they remove or release a photon of a certain specific wavelength. Electrons de-excite and release photons in random direction. This is the key part which causes these dark lines, because you didn't get it back. It is now emitted in a random direction. You didn't get it. It's not received on the screen, hence a dark line is observed. Okay, part B. He says for hydrogen, these are energy levels. Okay, fine. These wavelengths are given to you just for the sake of understanding. If he asked you, or he hasn't, but if he asked you, he says these transitions are from N2. The formula is E equals to hc by lambda, which is actually delta E. So if this is E2 minus E1 equals to hc by lambda, if the change is much greater, then the wavelength is going to be much smaller. So if we discuss this 412, it starts its journey from N2, but since it's the smallest one, it should end its energy at the highest level, which should be N equals to 6 in this scenario, right? So the highest change in energy, highest delta E, gave rise to the smallest wavelength. Similarly, so from N2, these are consequently N5, N equals to 4, and then N equals to 3. So the smallest delta E was N2 to N3, produces the largest wavelength because they're inversely related, right? So this is the idea for this graph at least. Okay. In the next part, he says calculate the energy of the energy level N3. Has it given you the energy of another perspective or another energy? Yes. So at N2, it has minus 3.4. So this is minus 3.40, right? And as you go above, the energy requirement actually reduces. So this answer is going to be less than 3.4. Let's say it could be 1.5, it could be 1.6, it could be 2.0, but something less in terms of number in comparison to N number 2. So how to go about this question? So first we find out the change in energy level, finding it from the largest wavelength, right? This is why I discussed the previous answer. So this is going to be hc by lambda. So 6.63 into 10 raised to power minus 34 multiplied by 3 into 10 raised to power 8 speed of light divided by 658 into 10 raised to power minus 9. This gives me an energy of 227 into 10 raised to power minus 19 joules, right? Okay. This is the energy change if it goes from N2 to N3 or N3 to N2. Do we have the energy at level 2? Yes, we do. So change in energy is equal to E2 minus E1 equals to a number that is going to be 3.0227 into 10 raised to power minus 19. Because we went from this level to this level, some photon hc by lambda must have been emitted because of the difference of the energies, right? So that wavelength gave us a change in energy, that only this energy change can produce a specific wavelength. So today we have the energy at level 2, which would be negative. So negative energy at level 3 minus negative energy at level 2 equals to the change that took place, 3.0227 into 10 raised to the power minus 19. All right. Okay. So since we want to find for N3, this stays over here. This negative becomes multiplied with this negative becomes positive, right? So it goes over there and gets subtracted, right? So our En equals to 3. Notice also, this is actually electron volts, EV. So we have to convert 3.4 into 1.6 into 10 raised to the power minus 19. You multiply this to convert this into joules because our answers are also in joules, right? So this is also supposed to be negative, right? So when you do that, this answer comes out as negative 2.42 into 10 raised to the power minus 19 joules. So this is going to become minus 2.42 into 10 raised to the power minus 19, right? I hope that we understand this idea. Sorry, this is not going to be positive. This stays, sorry, this is negative, this stays positive. This positive becomes positive, right? Yeah, this is going to be negative. Yes, this is right now. Okay, moving on to the next question. So plutonium 238, complete the equation. Alpha is 42. This is from memory, and then we just subtract it. So this is going to be 234 minus 92. He says 0.874 plutonium, each nucleus decays and emits this much amount of energy and has a half-life of this one. Calculate the number of atoms of plutonium at the beginning. So it's going to be from N naught equals to moles multiplied by Avogadro's constant. So moles is mass over MR, and mass has to be in grams. So this is going to be 0.874 multiplied by 1000 divided by the MR, the molecular mass, which is 238 multiplied by Avogadro's number, 6.02 into 10 raised to the power 23. This is going to come out as 2.21 into 10 raised to the power 24, positive 24. So very huge number of atoms, very high radiation dosage, plus 24 number of atoms. Determine the initial activity. So this is A equals to lambda N. So activity is equal to lambda. Lambda is decay constant. So decay constant has an equation which is ln of 2 divided by half-life, right? So that will be ln of 2 divided by half-life is 87.7 years. Activity is always in per second. So 87.7 multiplied by, yep, so multiplied by, since it's in years, 365, 24 hours multiplied by 60, multiplied by 60, and then multiplied by the number of atoms, which is 2.21 into 10 raised to the power 24. So ln2, when you solve the whole equation, the whole system, the activity comes out as 5.538 into 10 raised to the power 14 becquerel, BQ. So this is going to be 5.53 10 raised to the power minus 14, sorry, positive 14. Unit is becquerel. Now what is becquerel? So 1 becquerel is equal to 1 radiation per second. So basically 5.5 raised to the power 14 atoms or molecules are undergoing this radiation, undergoing this radioactive process, emitting this many number of alpha particles and uranium atoms. Use your answer in B2 to determine the initial power output. So power is equal to energy or work done divided by time taken for the process. Now we know that the current activity is this much today. These atoms are being released each second. So we have figured out the time, which is going to be 1 second, but we need to figure out the energy. So one atom, if undergoes this decay process, releases 5.5 mega electron volts, right? So if it releases 5.59 mega electron volts in 1 second or in one reaction, how many should it release? How much energy should it release if these many atoms are being released? So first of all, the energy, which is 5.59 into 10 raised to the power 6 for mega electron volt conversion, becomes 1.6 minus 19. Then the number of atoms that are doing this. So 5.54 into 10 is to the power 14 radiations, atoms released, divided by in 1 second. So the whole system is being divided by 1. So it automatically becomes energy divided by time. So the answer comes out as 495.4 watts, which becomes 496, but you can say 495, right? So the space probe will continue to function until the power output of the plutonium decreases to 65% of the initial value. He says, calculate how long it can operate at its capacity. So the output of plutonium, you see we have an equation or decay equation related to this, which is x equals to x naught e raised to the power minus lambda lambda t, right? This x could be activity, number of atoms, or radiation, right? So if it reduces to 65.3, since the number of atoms, or you can say that the activity, you can simply put over here that this was activity, so power was equal to the energy of one reaction multiplied by the activity, right? So power is dependent on activity, so power is dependent or proportional to activity. So if we're discussing power decrease, then we can replace it in terms of activity, no issues in that. So A is equal to A naught e raised to the power minus lambda t. This t is what we want to find out because lambda is a constant, decay constant, reduces to 65.3. So today, currently, it should be 0.653 of the initial value, A naught, if the initial value was 100%, which was 1, multiplied by E negative lambda by t. You take the ln, this A naught gets cancelled out. You take the ln of 653 equals to this ln E, and lambda t comes out, and this becomes negative lambda t. And lambda, of course, is ln2 divided by the half-life, which is, since the answer is supposed to be in years, this will be taken as in years, half-life, right? So this t is now equal to, the negative cancels out automatically because this is a negative answer is going to be as well. So ln of 0.653 divided by ln of 2 divided by 87.7. Yeah, so this is going to be t. So t comes out as 53.9 years. So it will keep on operating for 53.9 years or 54 years, up to 2 significant, because we can't take 2 significant because it's a nuclear reaction, and 53.9 actually means something. How many number of years and months and days this is going to be, we have to be very specific about that. So it can feed the system for 53 years for its power requirement. He says we have an alternative with a half-life of 0.38 years, but a smaller mass would be required for this one. So state one advantage, smaller overall mass, so the satellite would have a less overall mass. It will be easier to subject, or easier to launch into space. It will have a shorter half-life, so it will not be able to provide energy as long as the previous plutonium, the 238 probably. Yes, it was plutonium 238, I think. Yes. So 238 half-life was 87 years, but 210's half-life is only 0.387 years, 37, not even a full year. So it will lose its power much earlier, much sooner. The next question is about explain how ultrasounds are detected. So it's done by piezoelectric crystals. They get information from the reflected boundary, change their shape, and produce an induced EMF. You see, piezoelectric crystals, if you change their shape or you apply a very large amount of force, due to the change in shape, they experience an EMF. So sometimes they produce a positive and negative potential. Sometimes they produce a negative and positive potential depending upon how you change their shape. So since their shape changes because of the application of force and they produce an EMF, this is the idea behind the ultrasound machine. So this is the piezoelectric crystal placed over here. So we introduce an ultrasound. It bounces from the boundary. Some is transmitted, some is bounced back. So when it comes back and is detected by the ultrasonic sensor, this changes shape. Sometimes vibrates to become this, and sometimes vibrates to become this. Why? Because sound is a compression and rarefaction, compression and rarefaction. So it keeps on oscillating between these two shapes. When it does so, this information is fed to a computer that reads this changing EMF and produces an image. So that is what we've written down over here. You can pause the video, read the answer, and it will make sense to you, right? Okay, so I'm going to erase this because I have to use this diagram for the next parts. So he says we have an equation of that varying EMF detected by the ultrasonic sensor. He says that the RMS is 66 volts and the frequency is 4.3 megahertz. He says V naught, the maximum amplitude. So we have this from AC electricity, that V naught is actually equal to under root 2 times the RMS value. So this becomes 93 probably. It's 93.3. So this is 93.3 volts up to two significant figure. This becomes 93. Omega is equal to 2 pi F. So that is going to become 2 pi into 4.3 into 10 raised to power 6. Mega is 10 raised to power 6. So this becomes 2.7 into 10 raised to power 7 radians per second. 2.7 power 7. Next he says complete the table. So the units are going to be kg, m minus 2, s minus 1. This is from AS basically. So we basically the specific acoustic impedance is multiplication of density and speed. So density is kg, m minus 3. Speed is ms minus 1. So 1 m cancels out. So we are left with kg, m minus 2 and s minus 1. That is what the unit is going to be. Okay. All right. Then he says to write down the value of the density of the soft tissue is fine. So we have the multiplication answer. So Z equals to rho C. So 1.7 into 10 raised to power 6, which is this value. Then we have the speed of the medium, which is 1600 multiplied by the density, which is unknown. So density comes out as 1062 kg per meter cube. So this is going to be 1100. So you can write down 1100 over here. Then he says use the data from table 9.1, use or refer to the values and tell me why an image cannot be produced inside the air cavity, such as lungs. Why we can't use it to see an image of inside the lungs. We can see the image from outside the lungs, but we can't see it from the inside. We can't see the small bubbles that are inside the lungs, which actually store the oxygen. So why is that so? So first, we need to understand the reflection coefficient formula. So the reflection coefficient formula is IR divided by I naught equals to Z1 minus Z2 divided by Z1 plus Z2 whole square. This IR is the reflection coefficient. This is that reflected wave, which is IR. And this is the transmitted wave, which is IT, which was sent into the system, right? Now, notice that if you take this I naught over there, then IR is equal to I naught multiplied by this reflection coefficient. Let's call this alpha. If the bracket's answer is equal to 1, if this whole bracket is equal to 1, what does that mean? It means that the incident wave, which was I naught, is completely reflected back. Nothing was transmitted, right? And if this bracket is less than 1, or you can say it is much, much less than 1, so that means that the reflection of, let's say, I naught, let's say this answer is 0.2. So only 20% of the initial wave that was introduced is reflected back and 80% was sent in. This is what we want, right? So we want minimum reflection. We want minimum reflection if we want to access a certain organ at a certain depth. Now, over here, he says why an image can't be produced. Now, you can see that there is a large difference between the acoustic impedances of air and soft tissue, power 2 and power 6. So you mentioned that the Z tissue or the impedance of tissue is much, much greater than the air. So the reflection coefficient becomes nearly 1. This is what I discussed earlier. Even if you put in the values in this formula, you will see that the whole bracket becomes 1. Since it becomes 1, it means that the whole wave is going to get reflected back. If you send something, if you send a signal and you receive it back, nothing was transmitted. So you can't access the organs that are inside the body. If you can't access them, will you be able to see them? You can't see them. So not transmitted. If there is no transmission, then no wave reflects back, so no image can be formed. So inside the lungs, it will not be able to penetrate. If these are the lungs on the outside, there is air on the inside, the whole wave is going to come back and we can't see something inside. We can't be able to see something or the air pockets inside the lungs, primarily because of this reason. All right, a student observes different stars. This is a repeated question. Give 2 reasons why some stars appear brighter than the others. So star may be closer to the earth, that's why they're appearing brighter, and some of them or the stars may have greater luminosity, that's why they're appearing brighter. Standard candle, standard definition, objects of known luminosity. Please memorize this. He says that observed lines, spectral lines from the star, observed 660. The same spectral line in laboratory are at 656. And the speed of the star moving away from the Earth is this one. He says, show that. So the formula that we have for this is actually delta lambda divided by lambda is equal to V divided by C. So we want to show the speed, right? So delta lambda is going to be 660.9 minus 656.3 divided by the standard value. What should be the standard? Should it be 660 or should it be 656? It is 656. Why? Because it was observed in the laboratory. It was observed on Earth. It was observed on the ground, right? From our star, which is the closest star to us, our own sun. And the same spectral line from the distant galaxy was observed at 660, right? And definitely, since we know that due to redshift, the wavelength increases, this wave is coming from a distant star, this wave is coming from a closer star. Equals to, or partially equal to, or approximately equal to V divided by speed of light, which is 3 into 10 to the power 8. When you take this over there, you don't need to add the nanometers, because in the numerator that is nanometer, in the denominator that is nanometer, so it will cancel out. V comes out as 2.1 power 6, which is what we were supposed to show. It says calculate the distance, so we have the Hubble's law as V equals to H naught D. So speed was 2.1, sorry, is it 2.1? Yes, 2.1 into 10 to the power 6. Hubble constant is 2.3, power minus 18 into D. Where is this galaxy located? How far away is it from us? So to 9.13 into 10 to the power 23 meters. It is very, very far away. Power 23, very far away. So state what can be concluded about universe based on the changes in observed wavelength. So Doppler effect. So since the wavelength increases, or the change in wavelength increases, the wavelengths are red shifted. Stars are moving away from the observer, from the Earth. On Earth, hence the universe is expanding according to the Doppler effect. There is a specific answer for this, specific answer for universe expansion, the Big Bang theory, and the rest of the question. So you're supposed to memorize it as well. That's the end of the paper. I hope you understood the quote. I hope you found the solution to the questions you were looking for.